Welcome to the webinar, everyone. It is 12 o'clock, so let's get started. My name is Ashley Stromack, and I am a Customer Engagement Specialist here at Test Oil. I'd like to thank everyone for joining us today. Just a couple of things before we get started. I wanted to let you know that everyone is on mute for this presentation. If you have questions throughout, please feel free to use the questions box on the GoToWebinar application. Everyone is on mute because we are recording this. The recording will be available later on today. You'll be emailed a survey with the recording attached. Today's presentation is titled Taking a Deeper Dive to Identify Mysterious Material. And our presenter today is Heather Versillo. Heather is a certified lubrication specialist and is a data analyst for Test Oil. Heather has played a significant role in Test Oil's technical operations department, where she developed the material identification analysis and deposit classification tests to determine the root cause of machine and lubricant failure. Heather has been a guest presenter at several industry events hosted by entities such as NORIA and STLE, where she discussed these specialized test methods and root cause analysis practices. She has hosted several webinars and training sessions with the goal of helping customers better understand their lubrication system. Heather, if you're all set, why don't you take over from here?
All right, thank you for the introduction, Ashley, and good afternoon, everyone. As Ashley mentioned, I've been kind of lucky enough here at Test Oil to have been involved in a few different departments here. The materials identification analysis testing, which we're going to be discussing during this webinar today, I was able to have a pretty large part in helping develop that and get that going when I was part of our technical operations department. And actually, since then, I am now in our data analyst department. So it's been kind of an interesting transition where I went from working with the MIA and really getting to the nitty-gritty problems and what are the nitty-gritty causes of those problems to seeing these overall routine testing and seeing how this relates to the big picture of the routine testing that probably most of you see. So with that, basically with this webinar, we're first going to be discussing what the testing really is, how we kind of go about doing it, and the applications. And then from there, we're going to end with a multiple case studies to give you a better feel, hopefully, of what this type of testing is really applicable for. So with that, we built this webinar really as a means to help further plan, figure out what is really happening when things aren't working quite the way they should. And maybe routine analyses is having difficulty pinpointing these issues. And there are multiple reasons for that, which we'll also get into today. So really, what is the materials identification analysis, or MIA test? It's really just a forensic investigation of any sort of problematic or foreign material that might be found in the system. Many of you have probably experienced any sort of machine component issues, whether it be bearings or servo valves or heat exchangers. Then going on to filters where you have a high differential or you find filters plugged with some deep dark brown sludge. You might have grease contamination. Other examples are potentially incompatible lubricants. Maybe you have a mixture of a mineral oil and a phosphate ester, or vice versa, where there is a silicate ester that gets into the system somehow. And these types of lube incompatibilities can often result in viscosity issues, but high viscosity can also be due to degradation of the lubricant. So how do we tell which is which exactly? And then lubricant incompatibility can also be related to reaction products between the two fluids. For example, I once had someone that actually added fertilizer on purpose to a tractor rather than oil. So you can imagine how much fun that was for our customer. And then there are hydrolysis reactions, which are a little bit more expected, more so than sabotage at least. And these actually occur when lubricants react with water, and it often results in a very sticky mess. So the MIA, on top of all those different kinds of issues that we're going to be looking to solve and figure out what's going on, it's really more of a one-off test, meaning that it's non-routine. And what makes it so non-routine is that the testing agenda really is quite unique to each sample. There's quite a bit of research that goes into this type of testing. There's a lot of contact with the customers to find out the environment that the machine or the system is operating in, potential contaminants within the area, sample handling practices, or even lubricant handling practices just within the plant itself. And one of the reasons we get so involved with the customers on these is to really try and pinpoint what's going on. We're not as familiar with your systems. You guys are all the ones that are on the battlefield day in, day out, working with the systems, knowing the little kind of unique ebbs and flows of each system. And that type of information is something that's really helpful to the lab when we're trying to assess what really is going on here. Something else when we're talking about MIA is it's really important for us to have the correct lubricant information, because when you really think about it, there are really potentially some 10,000 oils worldwide, and even more when you realize that people like to mix them in the same tank, whether it's on purpose or not. So with that, then on top of all of that, we're looking at advanced data interpretation. So we're really going to dig into the numbers and the data that we see to figure out what is going on here. So as a summary, this test was really developed maybe over a few years, 2 or 3 years ago. And since then, this has really been one of our favorite things to work on. It's pretty fun for us. Unfortunately, not always so much for the plant. It generally means they have some sort of problem. But we've also been really lucky in that we've gotten to dig a little bit deeper and get to know our customers a little bit better through this. And we've gotten to see some very strange things, such as duct tape or twine and green jello. Not really green jello, but you'll see a picture of that in just a second here, and I'll explain that. So why do we do this testing? Really, what we were finding a few years back is that we would constantly have customers sending in sludge or what appeared to be grease but was not grease, or just any sort of strange substance, and asking, what is this? Can you tell us what this is? And we were finding that our standard routine or fluid testing was not really able to either handle the sample or not able to reveal or pinpoint the specific problem. It could have been that a filter was experiencing a high differential pressure. There was buildup on the bearings, and actually that bottom right-hand picture there, that's a perfect example of that. And the picture makes it look a little bit darker, but in person that was quite green, and what we refer to as the green jello sample. Another example, there might be sludge on some walls. You know, these routine tests were created to handle our lubricant samples, which are assumed to be liquid. And many of the instruments are optimized for liquid samples and have components that are only meant to handle liquids. So many of the instruments are really just physically not able to handle sludge or two-phase samples or solids. So since these samples generally cannot be physically tested by the instrument, or they could even cause damage to the instrument, that was part of the big reason that we decided we need to find something else to figure this out. So examples of samples that would not be appropriate for routine testing but may have been more appropriate for materials identification analysis would be if the sample hold was more sludge than lube. You can see an example of that in the top right picture there. Because with the MIA, we allow for a better separation of the contaminants from the actual lubricant itself. Also solids. As we all know, lubes are supposed to be liquid, so the routine test packages are more geared towards that type of material. Sometimes we've also found that high water content can cause an issue. Probably many of you know that if you have extreme water or excessive amounts of water in the system, that viscosity results can be invalid. FTIR results can often be falsely high because it's seeing the water as potentially oxidation or other parameters, but it's more of a falsely high result due to all that water in the system. And then there are the machine and lubricant issues. So getting a little bit more specific on this as to why we do it too, apart from some pitfalls in routine testing. And don't get me wrong, routine testing is, we find many, many problems and are able to prevent many issues through that. But sometimes there's just holes that need to be filled in, and this is where that test kind of comes into play. So with the MIA, we really have the ability to detect many contaminants that routine analyses might not be able to pinpoint, as we mentioned. And routine testing might be able to give us an idea, though. So when we look at MIA, it can really pinpoint a number of root causes, whether it be leaks such as the coolant, NOx compressor, ammonia compressors. If there are thermal events occurring, maybe there's soot in a hydraulic system or electrostatic discharge. You might have microdieseling or coking. And with the MIA test, occasionally we can see chemistry that's related to the material formed before coking actually occurs in the fluid. So there's a little bit of a preventative measure there. In addition, we can see external contamination, whether that be dirt or water or lubricant was added that should not be in that system, potentially cloth or seal material. And these types of external contamination really inhibit fluid and machine lifespan. And then on top of that, we can also see fluid degradation materials. So whether that be esters or carboxylic acids due to oxidation of the fluid, hydrolysis reactions due to the presence of water, or additives such as ZDDP or PANA precipitating out of solution, once the fluid begins to degrade. And once these additives precipitate out, they might not be doing their job as well as they needed to be doing that. So the fluid's lifespan can be severely inhibited at that point, and thus the equipment. So one example that I kind of have of this is, before we get to all the really interesting case studies, is I actually had a cat transmission that had leaking ball seals, and we kept finding calcium carbonate, but we couldn't figure out where this large amount of calcium carbonate was coming from. So this is also a prime example of why we contact our customers so frequently and try to get as much information from them as we can with this testing, is that once we spoke with the customer about this, we actually found that the vehicle was working in a limestone quarry. So we were having a dirt ingression problem that was really compromising the seals, and calcium carbonate, once we learned it was working in a limestone quarry, which is calcium carbonate, we said, oh, okay, that's completely explainable where this issue is coming from now. So once we were able to figure that out, our customer was able to take proactive action to improve the life and performance of the lubricants in the machines in this quarry to prevent future issues. So this slide is really just an example of all sorts of different types of samples and materials that we've had come into the lab. So as you can see here, we have quite a few filters with sludge on them. We have jars of just sludge that come in, samples of lubricant, what looks like almost a film in some of these samples that have multiple phases or layers in them. We even have basket strainers. And, you know, we get other types of examples even beyond this. So this is just really a kind of overall of some things that we've seen come in. So we have throughout this, there's just a couple questions to let you all think about for a minute. So multiple choice questions though, not too hard. But first one here, Tesla offers filter debris analysis for FDA for filters. When should FDA be used rather than MIA? A, you're interested in the composition of metallic particles. B, the filter has a visible layer of sludge. C, there's a high differential pressure across the filter. D, you are concerned about the wear metal generation rate. E, A, and D. And the reason we ask this question is there seems to be a lot of confusion of whether to send filters for filter debris analysis or material identification analysis. I'll let you all think about this for a couple seconds, and we'll get to the answer. All right, so our answer is A and D. You're interested in the composition of the metallic particles, and you are concerned about the wear metal generation rate. So we'll find out in the following slides a little bit more about the differences between the MIA and FDA testing of filters, just to help provide some clarification. So every filter that comes into our lab is actually visually inspected, no matter what test it was sent in for, whether it was sent in for filter debris analysis or materials identification analysis. And the reason for this is that then we can see if there's any obvious issue that one test or the other would better identify what is happening in the system or accomplish the goals of that customer. Sometimes we also will send a requisition form asking some more specific questions about the customer's concerns and goals of the analysis. And based on that alone, sometimes their goal of what they need to know or want to know can help us decide which testing is the best fit for that customer to get them the answers that they need. So really, when we talk about filter debris analysis, we're trying to gain a comprehensive assessment of the machine wear that may be occurring in the system. And it can help us provide advanced warning of abnormal wear and critical operation through trending. And we can predict component wear in our critical rotating equipment through trending of this type of testing, and hopefully identify any impending failure of machine components. And really, this test is geared towards detecting wear metals. So we're looking for if there's an issue with potentially damaged bearing, metal piping corrosion, or if a pump is wearing. So really the bottom line is that this test is best for trending and issues due solely to metallic debris or machine component wear or damage. And the reason for that is really that this test uses EDXRF spectroscopy to identify substances contaminating the filter. And this instrument is really great at detecting inorganic elements in metals, such as your hard metals that are pretty typical of our machines, such as iron, copper, tin. But it's also really good at detecting inorganic soft metals, things like calcium, aluminum, silicon. However, it's not great at detecting organic materials such as oxidation or thermal degradation, plastics, RNO additive, etc. And really, many of these organic materials are composed primarily of carbon, hydrogen, potentially nitrogen, and other elements that this type of instrument just does not detect. So that's a briefing on the filter debris analysis test. So now when we move to MIA and we're talking about filters, this really is very invasive testing, which means that the filter is actually going to be disassembled so that we can physically view the different media layers, inspect the supports, and identify potentially multiple contaminants that we may need to isolate in order to better characterize them. So with this, we're going to be using multiple techniques. And unlike FDA, many of the different analytical chemistry techniques and instruments that are employed to gain a well-rounded understanding of the contaminants are going to be able to look at the inorganic, metallic, and organic characteristics of the contaminating material. So we mentioned a little earlier, but some of the abilities to detect are materials along the line of varnish that might be due to oxidation or thermal degradation or additive dropout, bacterial growth, or rubber that could indicate gaskets or seals have been compromised, damaged bearings, or an inorganic salt that could have been formed from the combination of oxidation byproducts and metal ions floating in the oil. And then also sometimes we see glycol contamination or even other strange types of materials such as fertilizer. So now that we know a little bit more, we're going to be looking at, have another question here. A brown sludge is found plugging a filter. What is it? A, varnish, B, thermal decomposition of the fluid, C, bacteria, D, who knows? I'll give you a couple seconds to think about this one. So the answer is D, who knows? And part of the reason for that is noting the color and consistency and smell as well as other observations can really give us clues as to what might be occurring. However, I never recommend identifying an issue or being 100% certain that an issue is related to this based on those types of observations. As you can see in the slide here, we have two filters that both had a brown sludge that was actually causing a high differential pressure across the filter. However, the reason for the brown sludge is very different. On the top filter, we actually have a fuel filter, and that is bacteria that's actually coating the fuel filter. And on the bottom, we actually have a system that was due for new charge of fluid, and during the cleaning process, the cleaner was not completely moved, and it actually reacted with the lubricant to form this brown sludge that was being caught by the filter. This is a prime example of why you never want to just go based solely on the color. We have so many questions almost on a weekly basis of why is my oil dark in color, or why is this color? And I just like to bring up this point that just because it's a certain color doesn't mean it's one certain thing. There are many, many different types of issues that could be causing color changes. So at this point now, we're moving on to our case study. And I believe we have about 5 of them in here. So in our first case study here, we actually received a lovely bag of sludge. And this bag of sludge is from a turbine at a geothermal power plant that experienced a catastrophic failure. So upon receiving this, they requested that we identify the sludge and where it came from. And the first thing we always do with samples really is we try to isolate them into different test tubes. One, we try to isolate any organic material and any inorganic material, and then the lubricant itself. And the reason for that is we like to try to identify the lubricant itself just to ensure that the correct lubricant was actually in the system. So, because we see it all the time where we are told by a customer that lubricant A is in the system, and we're like, well, you know, from what we're seeing, it really looks like lubricant C is in there. So we just like to try to confirm that information, because if they believe that there is one type of lubricant in there, but really it's a different, that could be the root cause of the issues itself. So going back to this case study now, what we found here was in the organic portion, we actually found many different types of chemistries. We found water, although the sample, there was a lot of water. Water was kind of everywhere here. Carboxylic acid and ester. And these types of materials, the carboxylic acid and ester, are typically attributed to the formation of varnish in the system or degradation of the lubricant itself. And then we also found thermal oxidative compounds, which to us means that there were elevated temperatures in the system at the time, or overheating. So, you know, typical products of lubricant degradation due to oxidation in the presence of water. Nothing too exciting going on there. So then the inorganic portion, we found carboxylic acid salt. And more specifically, we found acetate and sorbate and sulfur. So this type of material typically forms when a metal ion, such as sulfur, or even calcium, sodium, or iron, is present in the system and bonds with the carboxylic acid that's a result of oxidation. So we were trying to determine where all these minerals were actually coming from, and found that they actually had a mineral water ingression problem. So from this, we were able to determine that the source of the issue was due to mineral water ingression problem. And at that point then, the customer, it was recommended that they needed to find out how this mineral water had ingressed into the system. Keep in mind it is a geothermal plant, so that was part of what they used to run. But they need to figure out which part of the system had failed to allow this to enter into and how to remedy that. But at least we were able to pinpoint them into what had caused this chain reaction of events, water had gotten into the system and then caused the lubricant to degrade, which created deposits in the system that prevented proper operation of the turbine. So moving on to our next study, we actually have here a system that was using a hydraulic ethylene glycol water-based fluid. And this filter came from a filter loop that actually had a pump on the same loop. And the pump had failed, so we did expect wear metals to be present. So this customer actually had the testing, filter debris analysis testing done first because they want to know exactly the metallics that were present from the pump and see what was, how extensive the damage was. And we ended up finding iron, nickel, and chromium, and unfortunately the damage was quite extensive, it appeared. So from there then, while we were able to identify the extent of the damage, then the customer wanted to know, okay, well, why did this damage occur? So then we moved on to material identification analysis, and we started looking at the organic material that we were able to pull out of this machine, or out of the filter media. And you can see that in the middle test tube picture there. And we found ethylene glycol, which is expected since the fluid in use was a ethylene glycol-based hydraulic fluid. But then we also found polyether ester, which meant that a surfactant was possibly filtered out. And surfactants are generally pretty large molecules, so it's not that uncommon that that could happen. And part of the issue is that depleted surfactant in the system could reduce the lubricity of the fluid, which may have been a factor in the failure. So then we also found silicate, which is really just related to dirt. And we also had a little bit of the polyethylene terephthalate. But keep in mind that polyethylene terephthalate, or PET, is the same exact material that the filter was made of, or portions of it at least. So that wasn't anything too interesting of a find that could have amounted to much other than saying that we had some fibers come out during our washing process of the filter media. But what was interesting then is that we did find silicone, and this, which indicated that there might have been a two-phase system going on, because the silicone oil, potentially grease, would not be expected to be compatible with the ethylene glycol lubricant. And incompatible fluids are known to form patchy deposits that can behave similar to varnish. So we suspected then that they had a two-phase system, a layer of silicone, a layer of the ethylene glycol, that probably impaired the proper pump operation. So at this point, unfortunately, there was no easy way to just isolate the silicone within the system and get it out and just continue with the ethylene glycol lubricant they had. But most likely they had to flush the system and charge it with a new fluid. But in the future, it was also recommended that routine oil analysis was used, because this is a problem that most likely could have been detected by routine oil analysis if they had used it. So while we get some pretty small filters here for testing, we also get some pretty large filters, as you can see here. This one's halfway up the door. This one's actually a diesel fuel filter that came in with a sticky resin, which you can see really well in that top right picture. And these filters were plugging within 24 hours. And I was told by the customer that they were using 1 gallon of additive for every 1,000 gallons of fuel, which worked out to be a concentration of 0.001%. So while going through our washing process of the filter media, we found degradation products of the fuel. We found carboxylic acid. But then we also found quite a bit of an EVA additive degradation products, which are materials such as olefins and carboxylates. So really, the sticky resin we found was a combination of carboxylic acid, which resulted from degradation of the fuel itself, water, and EVA, the fuel additive degradation product. And for that to come out, it really suggested that this system had been improperly blended with the additive. And the improperly blended additive most likely resulted in a hydrolysis reaction with the water to cause this really, really sticky mess that the filters were catching. So really the recommendations with this were if they were to ensure that they were using proper blending practices. You want to make sure that you're avoiding splash blending because that is not going to mix it in well. So it really came down to how the additive was blended in this system. So with this case study then, we actually have a gear oil that was pulled from a gearbox. And the sample was originally sent for a routine test package. And this was definitely a case that a routine test package would not be appropriate or solve the problem. One, because it looks like there are multiple materials in this lubricant sample from the picture on the left. We have those kind of pink blobs, and then we saw white flakes and what looks like black strips and black flakes. So there's multiple materials there. And also it appeared that some of the materials were quite gelatinous or solid. So the routine analysis instruments just would not be able to handle that type of material. So we recommended materials identification analysis so that we could really dig into all the multiple contaminants that were present there. So we used elemental spectroscopy and viscosity to help characterize the oil itself to ensure that the correct oil was being used in the system. We found that it was. And then we started to identify the 3 different types of contaminants that we had here. So the first one we looked at were the black particles. And we ended up finding out that these were actually silicone rubber. Obviously, some sort of gasket or seal had been damaged and was actually destructive and flowing into the system from somewhere. Then we looked at the white particles. And we were able to identify those as an aromatic polyether compound, which is really a material that most likely formed from some type of resin that can often be found in coatings or adhesives. And then finally, we looked at those pink particles, and they were a combination of carboxylate salt and hydrocarbon stearate, which is really a soap-like chemistry that could indicate grease contamination had occurred in the system. Apart from that, we also ended up finding titanium, which is commonly used as a pipe brightener in many systems. So really it ended up that most likely they had a damaged silicone rubber gasket in here, and they had grease contamination that had occurred and was causing peeling or deterioration of any painted surfaces within the system. So the goal of the customer then was to go find where this gasket had come from and how to resolve the issue. Unfortunately, we were able to do a pretty decent job helping them with that. Okay, so on this next one, you can see that we have a nice kind of sample of sludge here. And this sample was, excuse me, primarily a dark gray and black sludge that would seem to be mixed with metallic particles. This was originally sent in because a bearing within the gearbox had failed, and they suspected that there was contamination from the silicone sealant. We ended up being able to determine through the analysis, though, that the system had been severely contaminated with silicone grease, and that it was also determined that the lubricant itself had experienced oxidation. However, this really wasn't the primary concern. The primary concern was the silicone grease that had most likely caused the bearing to fail, and the system would need to be thoroughly cleaned with a solvent in order to remove the contaminating silicone. And one of the big recommendations here was that it might have been worthwhile to consider investing in labyrinth seals if they weren't already in use. We never heard what exactly was being used, but it is pretty widely recognized that labyrinth seals have very good performance when compared to your standard lip seals. And that was really the big recommendation for this one. And also, routine testing on this may have been able to detect a silicone issue sooner. So then moving on to our next case study here. We actually have another sludge sample that was received from a generator. And this was a unit that operated 24 hours a day indoors in a pretty clean environment. And during an outage, the electrical crew needed to access the generator, and they're the ones that actually found this sludge material. So they scraped it from the generator and sent it in for analysis. And really, the goal of this analysis was to identify components of the sludge material and why the material had a brown coloring. So through the analysis, we first isolated out the different components, the lubricants, organic materials, and any inorganic materials. And we were able to find that during the analysis, there was glycol contamination, water contamination, oxidation products, and silicates. So the presence of the silicate really indicates to us that dirt was present in the system. Oxidation products indicates that the fluid itself had experienced degradation and was forming varnish. And then the water and glycol suggests that the system was contaminated with a coolant. And glycol and hydrocarbon fluids are known to not always be compatible, and this type of sludgy, sticky material is expected to result in deposits and impair the machine condition or machine operation. This type of deposit is also known to plug filters. So really, this was another system where it was recommended that the system needs to be flushed because there is really no other way to isolate out the glycol from the original hydrocarbon-based lubricants. Also, they needed to identify how glycol was getting into the system in order to prevent the contamination in the future. And then this sample here, or filter rather, is one of my favorites that I got to work on. It was one of our first material identification analyses. This filter, as you can see, is covered in what appear to be all sorts of different types of fibers. It looks like this thing was just wearing a sweater. So this filter was actually pulled from a polishing unit of a bottom roll hydraulic system, and the customers were seeing severe product contamination. So when they pulled it out, obviously they saw all these fibers that we can see on the slide here, and sent it in for analysis to identify what these fibers were, so they could figure out what happened to the system. And the filter appeared to be covered in a combination of rubber, fibers, and leather material, or what appeared almost looking like a brown leather material. And you can see the those individual components on the right-hand side of the slide there. So through identification, we were able to find out that these were a polypropylene rubber, polyethylene terephthalate, and a polytetrafluoroethylene, or more commonly Teflon. Later, we were able to tell them that this was some sort of cloth that had been dropped in the system, and some sort of cloth that has is really good at handling high heat based on the materials that were used in it. And our only thoughts at the time, other than there was some sort of maybe rag or cloth, was that what would make the most sense is that there was another filter in the system that was potentially damaged, and this filter was now catching that. That was our recommendation at the time, was to find out, investigate these other filters in the system that are upstream, and are they in okay condition? Because what else would make sense besides that, right? So then this customer calls back maybe a week later after this, and they actually informed us that they had a welder working on the machine and the welder actually dropped his shop cloth in a hatch and didn't notify the plant. Maybe he didn't know he had dropped it in, but basically the cloth had fallen in and the machine chewed it up, and this was the result of it. But at least for the customer, the filter did its job, collected all the different fibers and particles, but unfortunately they did have a little bit of damage there from any sort of the rubber gasket. But other than that, that is the end of the presentation today. So I want to thank you all for joining us, and please feel free to ask any questions.
All right, thanks, Heather. Okay, first question that I see here is this something that you would recommend if they sent in a sample and the normal test package didn't look appropriate?
Yes. I think it's probably the short answer. You want to look at if this material is if it's a liquid, then it might be more appropriate for routine testing. However, you have multiple phases in there, or it is any phase other than liquid, say a gelatinous or solid type phase or material, then material identification will probably be more appropriate.
Okay, and that's not something they need to request. It's something that we may offer them.
We've had it occur both ways, where we've had customers specifically request this testing. Then other times we've had people send in a sample and we take a look at it upon beginning to process it to go into the lab, and we say, oh, this doesn't seem like it's a good fit. So it goes a little bit of both ways.
Okay, and I see one other question here, but that would be best answered through email. All right, Heather's information is on the screen, so if you do have any further questions or if you would like more information, you can feel free to email her, or you can also contact myself. Okay, thank you for joining us, everyone, and have a great rest of your afternoon.
Thank you. Bye.
Thanks, Heather.